So let's start. This says section 1.2. Mr. Dueck, what happened to section 1.1? That was lab safety. This is going to be mostly a review of your Science 8, except a little more detailed. I wrote down here some vocabulary words. These are words that on your test I would have no problem asking you in some kind of a matching thing to define them or make sure you understand these words. So I put these here more as like part of your study guide. When you go back and you're looking through your notes, this is stuff you need to know. But we're actually going to jump in right here where it says chemistry. What are we going to learn? Well, ideally we're going to learn why water flows but ice doesn't, why fireworks are different colors. We're going to talk about the structure of the atom. We're going to learn how to use the super cool periodic table. The alphabet of the universe is what I call it. We're going to learn why table salt is really called sodium chloride. I showed you that yesterday, actually. And how to name other chemical compounds. So you may have heard all these chemical names. By the way, naming chemicals is really complicated. We're going to learn this much of it this year, the basics, and then at least you'll have kind of an understanding when you hear something of what it might be made up of. Why you can thaw and refreeze ice, but you can't uncook meat. Some important points. Most topics in chemistry build on what we've done in previous classes. So if I wanted to give you any bit of advice, don't fall behind. Don't fall behind. If you ask me what's the most important unit this year for success in Science 10, it's going to be the chemistry section. In fact, we're going to be looking later on this year at electricity. That doesn't show up in Science 10. We'll be looking later on this year at astronomy. That doesn't show up in Science 10. We'll be looking later on this year at cell biology. Doesn't show up in Science 10. But this, in fact, the first unit in Science 10 is Science 9 chemistry done in about 2 weeks instead of a month and a half. Many people consider this to be one of the toughest units. Yeah. It's one of the cooler ones, too. I'm here nearly every day after school, so if you have a question, the last thing, Mason, that you want to do is put it off, put it off, put it off, put it off. Often it's going to be like one thing. And, oh! So that's why this, and the dominoes fall into place, or I showed you that picture earlier of the road to success, right? You ready to go? Good. Matter. Matter. Matter is anything that has mass and volume. I think now we're filling in blanks, yeah? Yeah. Matter is anything that has mass and volume. What's mass? That's far more complicated. That's, believe it or not, part of why they built the Large Hadron Collider. You may have heard a couple of years ago they were looking for the Higgs boson particle, which we believe might explain why some objects are heavier than other objects. So we're not going to get into that. Einstein did a little bit of that, but that's really detailed. For now, for you guys, mass is something that's heavy. Well, actually, no, we can be more specific. Mass is the amount, that's an M, of matter in a substance, and it's often measured in grams or kilograms. Look up. I've already told you I tend to abbreviate. If I had done this, you guys, you seen those symbols before? Feel free. I'm going to do that. Volume is the amount of space. Nice. I heard somebody even say it. A substance occupies. What's the metric measurement for volume? It begins with the letter L. Your milk is also measured in it. Okay, liters. Now look up. There is an abbreviation for liter. It's a lowercase l. Here's the problem. I also teach math. If I write that, what does that look like? Could be. So I will always, whenever I do a lowercase l, I'll always do it as a little, like a loopy, a handwritten one, just a habit. Oh, and look up. That's a plus sign. That's a lowercase t. I'll always add a little curvy thing.
We are now going to ask grade 11 students.
Pause for a second. So just a couple, as you're learning my atrocious handwriting, things that I try to do to be clear. We have something that we call the particle model of matter, and this is going to be a review from grade 8 in theory. In theory in grade 8, nice yawn, in theory in grade 8, you learned that matter is made up of particles. Turn the page. And there are spaces between the particles. Very small. They feel solid, but there are spaces between them. And there are two key ideas in the particle theory of matter. The first one is the particles are always moving. And the second one is the particles are attracted to one another, which is why stuff of the same substance tends to stay together. Well, Cheerios are made up of multiple substances, but I would say, for example, like a block of iron, of pure iron, it wants to stay with its neighbors. Okay? Then you also learned the states of matter. So what are the three main states of matter? By the way, there's more than 3 states of matter. If your teacher told you there was only 3, they weren't quite correct. There's a 4th one that I'll talk about, which is way cool. But what are the 3 main ones? First one begins with the letter S. Solid. Absolutely. That was pretty solid of you guys to remember solid. Now, what can we say about a solid? And I'm going to ask you this on a test, so you might want to underline this. Really, I think next year I'll leave this as blanks to fill in. You need to know that it has a definite shape and volume. And then as we go to different states of matter, that definite shape and volume might not be the case. Next one. Liquid. Liquids have a definite volume in that if you put them in a container and then you pour them into another bigger container, they don't fill up the bigger container more. But they have an indefinite shape. If you move them from a round beaker to a square beaker, they'll just take on the shape of the container, but they'll settle on the bottom and they have a definite volume. And then we had the third one. Gas. Gases have an indefinite shape in that they'll fill up any container you put them in, and they have an indefinite volume. If I put the gas into a bigger container, the molecules will spread out more and just fill up that bigger container. It'll take a bit. We call that process diffusion. It'll slowly diffuse through the rest of the room. Put your pencils down. Are there more states of matter than just those 3, solid, liquid, and gas? Yeah! Another cool one is plasma. Turns out the sun is made of plasma. Plasma occurs when an atom is in a situation where its electrons are ripped away and separated from the protons. You might not know what that means yet, but Danielle, you will know what that means in a little while. Okay? There are other cool states as well, but most of these only occur in a laboratory under extreme conditions, or, for example, in the very center of Jupiter, there's weird stuff going on there, or in the very center of the sun, because you got so much mass and heat and gravity. For all intents and purposes, Nick, we're going to pretend those don't really exist, even though they're nerdily cool. They don't show up in nature, at least not in the nature that we exist in. Next page, over. A chemical change is a change in matter that occurs when substances combine to form new substances. Explosives are great examples of chemical changes. But even baking is a good example of a chemical change. You add heat and something that might have been liquid and separate suddenly becomes something different or new. So this leads us to something that we call kinetic molecular theory. That's a lot of writing as far as I'm concerned, Maddie, so I'm going to abbreviate that as capital K, capital M, capital T. Can I do that? So when you see that, I mean kinetic molecular theory. There's 3 words there. Theory, means it's what we believe is true. Molecular, molecules. What does kinetic mean? Does anybody know? It means moving. So really this is saying what we think particles that move do and how they behave. Kinetic energy is the energy of motion. And the fact that all particles in every... Oh, hang on, another interruption. Got to pause the video.
Grade 11 students.
The fact that all particles in every solid, liquid, and gas are always moving means they have kinetic energy. And the kinetic molecular theory, the KMT, explains what happens to matter when the kinetic energy of particles changes. Now here's what it says. All matter is made up of very small particles. You said that already. I don't mind repeating myself. There is empty blank between particles. Space. Particles are constantly moving. Nice. And now let's look at the different situations. In a solid, the particles are so tightly crammed. You know, how about packed? Let's say packed, clumped, cramped. I'll go packed together that they can't move around freely. In fact, they can only, he mentioned it in the video, there was a word that began with V, vibrate. Nice. They have very blank kinetic energy. Little. Good. You guys are doing awesome. Then we have a liquid. In a liquid, particles are farther apart. And what this means is they can slide past each other, what we call flow. They can flow. They have a little more kinetic energy. In a gas, the particles are very far apart, and they move around very quickly. Nice. They have even more kinetic energy. In fact, here's the summary. The more kinetic energy the particles have, the faster they can move. And because they're moving around so fast and bumping into each other, the further apart they'll get. What's the easiest way to change the kinetic energy? Add and remove heat. There's other ways, but the easiest way, add or remove heat. So, if energy is put into a substance, it changes from a what to a what to a what? What has the least energy? Yes. I don't want to write solid, capital S. I don't want to write liquid, capital L. Oh, and that's why the sun is made of plasma, because if you keep adding energy to a gas, that's the next one on the list, but you got to get to a few million degrees before that happens, so it's not something you guys come across. What would the explanation be? Why would this happen? Because what's moving faster? Particles. Which means the distance between the particles when you add kinetic energy increases. Is greater, increases. The attraction between the particles, because they're further apart, decreases. Oh, and when you cool things, the reverse happens. I wrote down here, open your textbook to page 20 to see a lovely example. Did I paste this in your notes or not? Yeah. Let's open our textbooks to page 20. I'm going to pause the video. I included this diagram here because I'm also going to put it on your test for this unit. Except what I'm going to do is I'm going to have those words there blank, and it'll be like a fill in the blank kind of dealio. This is on page, I think, 21 in your textbook as well, in color, right? Okay. So I wrote down here, you should know all the terms that describe the changes of state. You can expect a question like this on chapter and unit tests. You should note that freezing and melting point are the same. The boiling point and the condensation point are also the same. It just depends on which direction you're going. Okay? So, all of you have a neighbor, except for one person, but I'll go deal with that. So look at your lab partner. Go to the reading check on page 21. You're going to take turns asking your partner the questions. In other words, the first person's going to ask their partner question number 1. Their partner's going to ask the first person question number 2, question number 3. You're going to take turns asking each other every other question. The person being asked must not only answer the question, they must convince the questioner that they are correct. And if they are wrong, they must correct it.